In this problem, we're asked to create the shear and bending moment diagrams for the overhang beam shown. We'll do this using the 5-step procedure that we established in Lecture 17, starting with determining the support reactions at A and B. So I'll draw a free body diagram of the beam. Show A, show B. It's 4 meters from A to B and 2 meters from B to C. And we'll show our distributed load with an equivalent force of 8 kilonewtons per meter times 6 meters, or 48 kilonewtons. Acting at 3 meters from the left end of the beam. We'll sum moments about A. Be the minus 48 times 3 for the 48 kilonewton force, its moment about A, plus B times the 4 meters, its distance from A, and we get B equals 36 kilonewtons. Now we can sum forces in the y direction. You get A sub y minus 48 plus 36, or A sub y equals 12 kilonewtons. Okay, so I'm going to put those over here in red. So we have 12 kilonewtons at A sub y and 36 kilonewtons, 36 kilonewtons at B. Okay, I don't know why I called that A sub y, it's just A. It does act in the y direction. Okay, so I have my first step of the procedure complete. I've shown all the forces acting on the beam. Now for my second step, I'm going to work from the left end of the beam where x equals 0. Okay, so let's see here. Now I'll put x equals 0 there, x equals 4 here, and x equals 6 at C. Okay, now I'm going to work my way from left to right and identify any discontinuities. And remember, we define discontinuities in the shear and bending moment functions as a concentrated force being applied, a moment being applied, or a distributed load changes value. So as I work my way from the left end of the beam, I have a distributed load that is not changing as I go from left to right. It's staying at a constant 8 kilonewtons per meter. And so I have no discontinuities from, and let me show what I'm doing here. I'm looking from starting over here at x equals 0, looking for values of x where discontinuities occur, and the first discontinuity is at b, where x equals 4, where I have a concentrated force of 36 kilonewtons acting upwards. So I'm going to need to write to create a free body diagram of the beam after taking a cut at some arbitrary point that is a distance of x from the left end of the beam between A and B, and solve for the shearing and moment functions for that segment of the beam. But before I do that, which would be step 3, I'm going to continue with step 2 and keep going from left to right, starting at x equals 4, and look for any more discontinuities. And I don't have any until I get to x equals 6, where the distributed load stops, so it changes value. And so I'll need to have look at the segment of the beam between x equals 4 and x equals 6 in a separate free body diagram, and establish the functions for the shear and bending moment for that segment of the beam also. So let's start with the free body diagram for the segment of the beam between 0 and 4. So I'm going to say FBD of x greater than or equal to 0 and less than 4. And I'm going to draw a free body diagram after I make a cut in the beam at some arbitrary distance x between 0 and 4. So let me make that cut here. And I will draw a free body diagram of the segment of the beam to the left of the cut. Okay, at the cut, I'm going to show shear force. Let me draw that better. Going to show the shear force acting downward, as I'm always going to do when I'm working from the left end of the beam, and show the moment acting counterclockwise. I have a 12 kilonewton force at A, and my distance to the cut is X. Now I need to account for the distributed load, and I'm going to show an equivalent concentrated load or force for that portion of the distributed load that acts over that segment of the beam, and that segment of the beam is X meters long. So my distributed load is going to act at the center of that segment of the beam, and its magnitude is going to be 8 times X kilonewtons. And its distance from the cut, it's acting at the center of the segment of the beam, its distance from the cut, I'm going to show it, ran out of room here, its distance from the cut is X over 2, because we know it's acting at the center of the segment of the beam. Okay, so now I can sum forces in the y direction for this segment. And I'm going to have the 12 kilonewtons minus 8x kilonewtons minus V, okay, I'm assuming that forces acting in the upwards direction are positive, and I solve that for V, and I get V equals minus 8x plus 12. So the shear function is a curve, well, it's a straight line that has a slope of -8, and I'm going to go ahead and graph that underneath the original figure of the beam here. And to do that, I'm going to establish an x-axis, and so this is x. This is where x equals 0. It's consistent with my numbers up under the beam. And I can assume some points here. In other words, in algebra we learned how to graph lines and parabolas and all that. So, but I like to just create a point table for these and plug in some values of x and see what values of v come out of that. So at x equals 0, v is going to be 12. At x equals 1, v is going to be 4. At x equals 2, v is going to be -4. At x equals 3, v is going to be -12. And at x equals 4, v is going to be -20. Okay, so v is going to vary from positive 12 kilonewtons down to -20 kilonewtons for this portion of the segment of the beam. So I will let, it's hard to see them here, but let's see, 1, 2, 3, 5. Here's -20. One, 2, 3. Here's +12. Now this is V, the V-axis, and we're in kilonewtons here. Okay, so now I plot these points. Zero, 12. I'm not going to plot all of them because I know I won't get them in a straight line. At x equals 2, well, let's do at x equals 4, it's -20. At x equals 2, v is -4. Let's see if I can get that. We know it's going to be a straight line. So at the halfway point there, I should be at -4. Okay. Then I'm going to connect those. And shade in the area between the curve and the x-axis. Okay, so that's the shear curve for the segment between 0 and 4 meters. Now I'm going to use the free body diagram and my moment equation to express the moment, the bending moment, as a function of x. So I'll go back to my free body diagram. I'll sum moments about to cut. And there I have set those equal to 0. And we're going to go down to the next line here. I have the 12 kilonewton force. Its moment about to cut is minus 12x. The distributed load force, concentrated force of 8x, its moment about to cut is 8x times x over 2. And then we have m. All that equals 0. I solve for m and do a little bit of algebra, and I get m equals minus 4x squared plus 12x, and that's quadratic. It's going to graph as a parabola, so we have to go back to what we learned in algebra 1, algebra 2, college algebra. Okay, now let me move the workspace up here a little bit. Let's do a point table for that moment equation. plug in some values of x and calculate the value of m so we can see what the curve looks like. When x equals 0, m equals 0. When x equals 1, m equals 8. When x equals 2, m equals 8. When x equals 3, m equals 0. And when x equals 4, m equals negative 16. Okay. Now we'll graph that. We'll do another x-axis down below the shear diagram. Okay. Our x equals 0 over here. M is going to be somewhere a little bit, its max is going to be a little bit more than 8. Notice between 1 and 2, the values of 1 and 2 for x equal 1 and 2 gave me the same value for the moment. So this is a parabola that's going to open downwards, and its max is going to occur between 1 and 2. Okay, so I will set up a scale here. We are in kilonewton meters for our moment scale. And on this side, we need to go down to negative 16. Okay, so I'll plot those points. I have 0. At 1, I'm at 8. At 2, I'm at 8. And at 3, I'm back at 0. And at 4, I'm at negative 16. Okay, now to find this point between x equals 1 and x equals 2, there's a point here somewhere that's the maximum value of the moment for this segment of the beam. And remember when we talked about the relation between shear and moment, we said that the slope of the moment diagram at any point x is equal to the shear at that point. Okay, well, at the max of a parabola, the slope is 0 at the max or the min. Should remember that again from previous algebra. And if the slope of the parabola is 0, if the slope of the moment curve is 0, then the shear must also be 0. Okay, so that's lining up, because look above that point there at the shear curve, and we see that the shear curve crosses 0, or is equal to 0, in that general vicinity. And we can find the value of x by setting the equation for the shear function, negative 8x equals 12, to 0 and solve for x, and we'll get 1.5. So that the shear curve crosses the x-axis at x equals 1.5. But then we can plug the 1.5 in to the equation for the moment. And for that, we will get to do that. I didn't have it pre-done. 1.5 x squared times negative 4 and add that to 12 times 1.5 and I get 9. So at x equals 1.5, the moment equals 9. So I'll put that in, and now I have that maximum point of the moment curve. Now I'm going to sketch in my curve, or try to. Remember, it's going to look like a parabola. Not too bad. Shade in the area between the curve and the x-axis. Okay. So now I have the moment diagram, the bending moment diagram for the segment of the beam between 0 and 4. Now I need to do the same thing for the next section of the beam. So I'll draw a free body diagram. Of the beam between 4 and 6 meters. Do that here. Okay. Again, working from the left, I'm always going to show the shear acting downwards. And the moment acting counterclockwise. I still have the 12 kilonewtons at the left end of the beam. Remember, I'm drawing the entire segment to the left of the cut, all the way back to x equals 0. Now I'm going to pick up that 36 kilonewton force, that support reaction force, at B. And it's 4 meters between those two forces. And the 8 kilonewton distributed load, I'm going to show just like I did on the previous free body diagram. I can represent that by a single force whose magnitude is 8x. Okay, and the distance from the left end of the beam, x equals 0, to the cut is always going to be x when we're using this process, which makes the distributed load resultant x over 2 from the cut, and the 36 kilonewton force is going to be x minus 4. Now these can be a little hard to see, but again, you have to always set the distance of the cut from the left end of the beam is always going to be x, and then the distances of the other forces or moments or whatever will be some function of x. Okay, so I've drawn the free body diagram of that. Now I'm going to sum forces in the y direction. And I have 12 minus 8x plus 36 minus v. So v for this section of the beam is going to equal negative 8x plus 48. Okay, and for this one, I'll graph that now. I'm just going to use two values. We know it's a straight line, so and we're starting this one at x equals 4. So when x equals 4, v equals 16. So we'll plot that, 4, and there's 16 there on the shear scale. And when x equals 6, the shear is back to 0. Okay. So that represents the shear in the segment of the beam between 4 and 6 meters. Now I'm going to write the moment equation. This one gets a little bit busy. I'm going to start it over here. Sum of the moments at the cut, counterclockwise positive, equals 0. Equals minus 12x, the moment of the 12 kilonewton force about to cut, plus 8x times x over 2. That's the resultant of the distributed load acting at the center of the segment, its moment about to cut, minus 36 times its distance from the cut, which is x minus 4, plus m. Okay, now you do some algebra there and you'll get that m equals minus 4x squared plus 48x minus 144. Okay, and I'll do a quick point table for that. We're starting at x equals 4. When x equals 4, the moment is minus 16, just by plugging in 4 into that moment function I just derived. When x equals 5, the moment is -4. When x equals 6, the moment is 0. So let's plot those. X equals 4, the moment is -16. It connects up to the previous moment curve. When x equals 5, it's at -4. And when x equals 6, it's up to 0. Now, again, we can use the relation between shear and moment. We notice that at x equals 6, the shear is equal to 0. Okay, so if the shear is equal to 0, the slope of the moment curve must also be 0. So that's where this parabola has a max. So we know that when we draw this, sketch this in, we don't have to be perfect with these, but we need to get the general shape. It's coming up and it's maxing right there. If it were to go further, it would start going down the other way. And we'll draw that in, shade that in. Okay, and so we now have what the problem requested was to create these shear and bending moment diagrams. We've shown them underneath the beam, which helps things be a little more intuitive. We use the fact that the slope of the moment diagram at any point x is equal to the shear at that value of x. And let's look at one more thing here. Let's look at the relation between distributed load and shear. We said in the lecture that the slope of the shear diagram is equal to the distributed load intensity. So if I move up a little bit here, the slope of both of the shear curves is -8. Okay. And that checks with our distributed load intensity, which is 8 acting downward, so we consider that negative. Okay, so you can use those relations between distributed load and shear and moment to help you create the diagrams, help you check the diagrams as a check on your work.